Welcome to Lab 2, Physics 155. This is electric fields and potential. To give you a little bit about the theory, in your Physics 1 course, Intro to Physics, you were given a potential energy formula, U, that was equal to mg delta H. So any object that had a delta H that was above the 0 point, usually it was the floor or a tabletop, that was the 0 point, had some potential energy. Okay, for instance, this marker, being above the table, has a certain potential energy. Okay. If I move that marker anywhere on the x-axis, let's say left or right, it has the same potential energy because I'm not changing the distance y, the height from the table. Similarly, I could be able to go in the z direction as well, and what that's going to make is a equipotential line on the x-axis, or it would make an equipotential plane in 3 dimensions. Okay? Meaning that anywhere on that plane, it has the same potential energy. Okay? This is the same with charged particles and electric fields. So if you have a charged particle, it will create a sphere of potential energy, any constant r that is away, radial distance away, similar to the y distance here. It would be a radial distance away, and it would be a spherical shell. Since we don't, that would be the equipotential surface. But we don't work in 3 dimensions here in the lab, so we're working in a 2-dimensional. So if you look at figure 2 in the lab manual, you'll see that it is then a concentric circle around the point charge. That's where your equipotential surfaces will be. It'll be these circular lines going outward at any specific constant r. It'll have a specific constant potential energy. Okay. We're going to set up the lab. Right now, as you can see, we have it set up for the simple geometry, which looks like figure 3. And we'll set up the measuring equipment now to make sure everything is working properly. Okay. So step 1 is set up our voltmeter. This is a voltmeter. Okay. It's actually a multimeter, but we're just using it as a voltmeter here in this lab. It says to set it for 20 volts. Okay. So put the dial on 20V, 20 volts. And it's already on DC, okay, for the DC current. Now we have a red lead that's attached to the voltmeter, and it's coming out of the V port. The red lead of this is attached to a probe, so we call it the red probe. We have the black wire coming out of the COM port on the voltmeter. That runs over here to another probe. Okay. Here we have a power supply. This is 1.2. We have a power supply here. We'll go ahead and turn that on with the switch on the side. This particular power supply, we don't need to worry about adjusting current on. It's already taken care of for us. And I will turn this up, according to this gauge, to about 5 volts. There's about 5 volts. Actually, it's a little bit, about there, 5 volts. Okay. And then 1.3, we'll measure the supply voltage from the power supply. Okay, so the supply voltage has this black lead that comes over to connect here to this connection. The red lead from the power supply comes to this connection. So what we're going to do is we'll hook the black lead from the voltmeter to the black lead of the power supply. We'll hook the red lead from the voltmeter to the red lead of the power supply. Okay. And we get about 4.41 volts is what is read by the voltmeter. Okay. If I take and reverse these, if I take the black lead and hook it to the red on the power supply, a little more table room here, and I take my red and I hook it to my black, you'll see we get the same voltage, 4.41, but this time it's negative. Okay, just means that we are reversing the voltage. We're reading it the other way. If I take both of these, both leads, and connect them to the same source, say the power supply, we get 0. Okay, it hasn't completed the circuit at all. It's reading from the same side, so there's 0 volts there. Okay. So that was 1.5. 1.6 will turn off the power supply. Section 2. Okay, we'll set up for the flat plate geometry. Okay. The multimeter we need to set back up the way it was. Okay, so what I'm going to do is I'll take this, the black side of the the multimeter, voltmeter, and I'll hook it up to the black terminal of the power supply. Now it goes through this little joint here and into this silver paint. Okay, so what I'm going to do is hook that black so that it's on the silver paint. Okay, that means this whole bar is going to be the negative side. Okay, this whole bar will have the same voltage as this black wire. Okay, this will be the negative side. Okay, so likewise, this red connection from the power supply is connected same bar to now this red side of the silver paint here on the red side of this. This is our positive voltage. Okay, 2.4, everything's connected back up. 2.4, we'll go ahead and turn on the power supply. I've left it alone, so it's right around that 5 volts again. And we're going to measure the voltage difference. Touch the probe now to the positive bar. Okay, touch that to the positive bar. And we get our 4.41. Okay, just as we would expect. That means we do have electricity flowing through the silver paint. The voltage should be less than the power supply is provided due to the resistance in the leads. As I said, I set this for 5, we're only reading 4.4. Because of all the connections, it loses some voltage along the way. Okay. Measure the distance between the bars, or measure X, the distance between bars with a ruler. We have the one bar here, the other bar here. Put a ruler between the two. This is also a good tip on rulers. You never want to measure from the end of a ruler. These get dropped and smushed and smashed and cut. Also, there's no 0 or 1 here at all on the end of the ruler. It makes it very, very difficult to read where 0 or 1 would be. So for this particular one, I'm going to start at 2, and I'll just measure over, and then I'll minus 2 from my number to get an accurate reading. Okay. So if I put that down at 2, this lines up to 10. So this distance between the two bars would be 8 centimeters, which you can see on the bottom here, they have measured it. These are in centimeters. Yeah, we started at, this one starts at 10, over at 18. Distance between the two would be 8 centimeters. Okay. You should be recording this all in your Excels. Read through section 2.5. You'll be able to record the voltage difference, V, and 2.6 is the measured X. Okay? Make sure to record that in meters and include units in your Excel, please. Okay, it makes it much easier for us to grade or to see where things went wrong. Next, section 2.7, go ahead and compute the electric field. Okay, so the electric field in that area is just going to be V divided by X, the two values that you had measured. And that'll be a constant value, or a constant field. So that would be the value for a constant field. Okay, you'll use this later in your lab write-ups. So make sure to make special note out of what the 2.7 is. Okay, section 3. Estimate the equipotential curves of flat plane geometry. Okay. Don't spend a lot of time on this section. We're just looking for basic knowledge. Okay. 3.1 says hand draw a map similar to figure 4 that just has the two bars with all these little plus signs or spaces in between. Okay. Hand draw that map. And then we're going to pick somewhere on the array and make a mental note of what that voltage is. And we'll circle it with a corresponding dot on your map. Okay, so I'm going to pick a spot. I will say right near the plus bar. Okay, I'm going to go 1 in, and I'll be down here towards the bottom. Okay, so we'll start there, and it reads 3.5, a little higher there. 3.54. Hold steady. Oh, there we go. That's what I wanted. 3.93, 3.94. Okay, right around there. It's even a little bit more. 3.95. Okay, 3.95 volts. That's our first point. We'll grab an adjacent point, and we'll see which adjacent point has similar voltage, and we'll circle that. Okay, so I was on this one. Let me grab the one. I guess on your video it's upper. Let me grab the upper one to that. We get 3.99, 3.97. Let me grab the one that was underneath it. .5. Okay, let me grab some that are over on the other side. Okay, the other side, heading towards the negative terminal. So here we get 3.4. Okay, if we keep going this direction, we get 2.8. If we keep going, 2.1, 1.73. 1.23 and 0.5. So you can see the voltage drops as I get towards the negative bar. Let's try picking a solid line here and see if we can find some that are close together. So this is the second one, this is the second one in from the positive. We get right around 3 volts. Go the one up from it, we get 3.1, 3.2. The next one up. Again, 3.1, 3.2, 3.2. Let me grab way up here, but all in the same row. Again, 3.3, 3.3, 3.2. All of these on this row are about the same. Okay, they do vary a little bit, but they are roughly the same. I'm not getting any 1s and 2s. I'm getting all right in the 3s. Okay. So based on that, if all the rows have the same voltage and they drop off as they go towards the negative bar, draw some equal potential lines where you think you would see the pattern. Okay? Draw a few of the lines using those measurements as a guide. Label them as field lines. They don't have to be straight, but make sure that they point in the correct direction. As the field lines go. Label your plot. You can label it simple geometry hand plot. That'll be just fine, because you'll have to make a plot again for the complicated geometry. Draw and label where your 0 and your positive voltage plates are. So make sure you identify this is the positive and this is the 0. Section 4. We'll measure the voltages of the first row. Okay. This measuring the first voltages here, this is going to give you, 13 values. Okay, so I'm going to measure this row here. It'll give you 13 values, and this is going to be in your data set. Okay. So I'll go ahead and I'll measure, starting with this one, all of these 13 values going up, and look for that in your data set. Okay, you'll be putting those into Excel, into a 13×7 matrix. And then we'll move on. That's actually section 4.1 and 4.2. 4.3, we will calculate the first row's average. Okay, if you're not sure how to calculate an average in Excel, the lab report does walk you through it. But you will create an average of that reading for voltage. 4.4, calculate the standard deviation. Again, look to the lab manual if you are confused on how to do standard deviation for that first row. And you'll also compute the percent uncertainty for that row. That was section 4.5. Now, the section 4.5 is special. It has a question in the back that you will need in your lab report. It says compare the average computed in 4.3 and the standard deviation in 4.4. Is the standard deviation value much less than your average value? Okay, so it might be a good time to look at the back page of the lab report. Look at the questions that you need to put in your lab report, because you can answer some of them now while it's fresh in your head. Okay, so look to those values. Is the standard deviation large compared to the average value, and what can you say about the accuracy of the measurements? Okay, tell me a little bit about it. Moving on to section 5, we're going to measure a few of the rest of the voltages. Okay, so to save time on this, we are just going to measure the center dot as we go along, and we'll type that into our averaged section of our Excel. Okay. We'll then copy that averaged value across to all the other cells to fill in. Okay. And if you're uncertain how to do that, look to section 5.2. And this will give you the averaged values of the other rows as we go across. Okay. So if you want just to check, you can look, and your numbers should be about what they are in the table given in section 5.3. Do not copy the numbers. These are not the correct numbers. The numbers that we give you in your data set are what we want you to use. So if you do have different numbers, it's okay. But you shouldn't have anything that varies much from these. For instance, the whole first row is around 4.5 volts in the example. If your first whole row is 18 volts somewhere in there, most likely that's a typo. Okay, that's not supposed to be there. So your values shouldn't vary much from the values that are given. Go on to section 6. We'll find the electric field in the flat plate. Okay, so now we'll measure the distance that is between the rows. Okay. Measure the distance between rows, that's your delta x. Okay. In between each of the rows, as we had already measured before, is 2 centimeters. 2 centimeters in between each of the rows. Record this value in Excel. 6.2. Compute the voltage between the rows. Okay, so you're going to take the voltage from one and minus from the other. Look to the lab manual, section 6.2. It'll walk you through how it wants to do it. You should have 6 values for this change in voltage, this delta V. Okay. 6.3 will compute the field between the first 2 rows. Okay, so using equation 3 given in the lab report, the electric field is equal to that change in voltage divided by the change in distance. Okay, calculate that. 6.4, compute the field for the rest of the rows. Okay, so follow the example that you would use for the first 2 rows and do it for the other delta V's. So just like you had 6 delta V's, you should have 6 electric field calculations. Okay. 6.5, calculate the average, the standard deviation, and the percent uncertainty of the electric field. So take those 6 values that you got for electric fields, average it, do a standard deviation, and find the percent uncertainty. Okay. This part also has to do with the questions in the lab report. In part 6.5, why were the percentage uncertainties in the electric field larger than the percent uncertainty in the first row? Gives you a hint. Is the difference in voltage smaller than the voltages in the first row? Okay, that's your hint. Answer that question in a short paragraph and explain your reasoning and why. Okay. The last question. The last question in the lab manual for your report says to compare the electric field calculated in 6.5 with that from 2.7. Okay, so we measured one and we calculated one. This is our comparison. We're comparing the two to see if they're within uncertainty of each other. Okay? Do they agree with uncertainty? And which do you think is more accurate and why? So the one we calculated with no uncertainty, it was just a quick calculation. We had measured it out. This one we took and broke it down into several parts and calculated the E from the average of that E with a standard deviation and an uncertainty. The standard deviation uncertainty. So I'll leave you to that to answer. Make it into a nice paragraph explaining everything as you go. Okay. Step 7, section 7, we're going to make a plot. You can make a plot in Excel using 7.1. It shows you which icons to select to go ahead and get your plot made. Section 7.2, you'll need to update the legend so that we know which parts of your plot are represented by your data. Okay? So just read through section 7.1.2 and make sure that your plot resembles figure 6. Okay? 7.3 has you print the plot because you're going to draw electric fields on it, or you're going to draw arrows on it. I'm fine with you just using a tablet, or you could even describe them if you didn't want to print and then have to like rescan in your Excel. You can, I'm sure there's a way to make arrows also in your Excel that would show that. But we do need to see your equipotential surfaces, your lines, your arrows pointing in the correct direction. All right, section 7.4, very important, to copy your entire Excel that you've made into a new one, because now we're going to do it for complicated geometry. Okay, so follow follow section 7.4 on how to do that. We've done it a couple times last year in the Physics 1 lab. So make sure you know how to do that. And we'll move on to section 8. Okay, section 8, I'm just going to turn the power supply off because I'm going to have to change this out for the complicated geometry. Okay, so our complicated geometry, this. Our complicated geometry has a big spot on it of conducting material. Okay, as you can see, we've made a big spot of conducting material. Now this will definitely change the equipotential lines. Okay, they will not be the same anymore. So 8.2, we're going to have you draw a map just like you did before in the previous section. Like the one in figure 4, this time you need to add your big circle in the middle and try and give us a map of the equipotential lines with the arrows. Basically, I need you to repeat part 3 of the lab. Okay. 8.3, adjust your Excel file. Take out the old values. Don't get confused, so just get those old values out of there, but leave any formulas that you left. And leave the plot. As you put in the new values into your matrix that you had made in Excel for the voltages, it will automatically update the plot. Okay. 8.4, obtain voltages of the new geometry. Okay, so in this one, we won't have these lines that are all the same. We can't just assume that the average takes care of an entire row. So we need to measure every single value this time in there, and that will also be in your data set. I will go through and measure every single value of this 13 by 7 array, which you'll be given in the data sheet. Okay. The surface plot, it should update on its own, created just as you did before if it went away. And also draw the field lines, okay, back on that plot. Okay. Once you're all done with that, I'll take care of the cleanup for you, and you can go ahead and submit your Excel. Make sure that your name is on it. Make sure all your calculations, all of your units are on it correctly, and begin on your lab write-up.